And before starting my talk, I want to present a little bit the people who do all this work, because obviously this is a long story, and many people are involved. And for instance, in red are all people listed which are in Brazil. So this shows that there's a strong French-Brazilian connection over many years. And in bold, these are people with whom I actively interact right now. So it's an ongoing active collaboration. Some collaborations are a little bit more sleepy, but we have to reactivate them. But it's a very nice collaboration, and that's why I'm so pleased to be here. The work I will present here is mainly done by, in the experiment by Guillaume Labéry and William Guérin now, and with the collaboration in previous time from David Wilkowski and Christian Minetera, and will be joined soon by Mathilde Fouché to join our group. And there's a PhD student from Brazil, and two other PhD students working on the random laser experiment, and one postdoc working on intensity correlations. And so to jump directly to my topic of my talk, so I will present first, in the first part, a little bit what I think is interesting in coherence of photons, and then I will come back to the atoms. Some of the parts which I will present have already been discussed this morning, or maybe this afternoon as well. So we'll see some doubles, but this is not a surprise, because we are here to celebrate the Year of the Light. So some things are obvious and landmarks or textbook experiments which are very important. So clearly we know that if you take a wave here which is hitting a slit, there will be diffraction. And if you look at the far field, you will have some ripples here, which are a signature of wave properties of this incident beam here. And this interference can be expressed in a typical young double slit experiment, where we know that the photons will go at the same time through both slits. Obviously, these are bad words to use, and experts know exactly why we are allowed to use these bad words to illustrate our purpose. For instance, if you take this picture here, which we have seen this morning, if you look at the single photon clicks on this screen here in an equivalent experiment, you would find the photon clicking here, here, and this could be understood like a particle going through one slit and hitting the screen somewhere. So this looks like particle trajectories. But if you build up many of those clicks, then you will find out that there's a structure in there, and this structure can be explained by wave properties. So in the same experiment, we have wave interference and particle trajectories, depending how you look at the experiment and what you really do in the detection scheme. This is in the lab, but there are also interferences everywhere outside the lab. For instance, if you take your two fingers and put them very close together and you try to focus on the object far behind, you will see like a dark line in the middle. You can see interference fringes like this. It's also been a topic on this, what is called the black drop on the Venus transit, which was important at some time to measure exactly distances, and you need to know exactly when Venus is entering the sun here or when it's leaving. And if you have like a blurred picture here, you might lose a little bit of precision. And all this is due to wave properties of light, even if it's coming from the sun. So you don't need a laser to do this. In both examples here, you don't need lasers to produce interference effects. They are omnipresent. Okay, so now the other question which we addressed in recent collaboration is, can we build up an explanation of interferences from ab initio, from individual atoms, from the atomic structure of the system? How can we reconstruct the response of a laser to a sample? And so if you zoom in on the material will be constituted of atoms, and in our case we take atoms which are in a cloud of laser-cooled samples, so they are far away. So it's not in condensed matter where the atoms really, the electronic orbitals overlap. So they're far away each other, and so each atom here will be excited by the external laser. Each electron on each atom will oscillate and radiate some field, and all these fields will make a big mass and interfere, and we can detect this in the far field outside here. So that's a scattered field out of a sample. So we can write down a microscopic equation how all these individual atoms respond to the external field. And here we see, so this is the evolution of the amplitude of each dipole, of each oscillator, which is excited by the external field, which the phase, depending on the position of the atom. And then there's some free evolution here, which depends on the detuning between the laser frequency and the two-level atomic resonance frequency, and then some natural decay time here, which corresponds to spontaneous emission. So this term here would be the evolution of each dipole if each atom were alone. But if I'm looking, for instance, at this dipole here, dipole J, it will see the light from the external laser, but also the light scattered by all the other dipoles, which will also excite a little bit this atom J. And this is expressed in this term here, which is a many-body term here, where all the dipoles are coupled together. So I can compute this numerically at least, and find the solution of the amplitude of each dipole in this large system of atoms. I can also compute ab initio the electric field, which is scattered in far field, and compute the intensity scattered by this cloud of n atoms. So I can build up the response of the system from individual atoms. So that's nice, we like this. We start from Hamiltonians, and then we build up the macroscopic response of the system. And so what we can do for a realistic experiment, for instance, we take a cloud of cold atoms, we come with a laser, and then we look where this light here is going. It can go in any direction. And so, for instance, in the forward direction here, this cloud of cold atoms, it's like a dielectric, it's like a lens. So this lens will take a plane wave and make it divergent or convergent depending on the sign of the index of refraction. And this is what I see here around the forward direction. I see this lensing effect, which can be explained by the refractive index of this cloud of atoms, like in the Mie field approach. But I also see some other light here which go around in other directions, which are the black dots here, which cannot be explained by just a simple index of refraction. And this can be explained by an incoherent model like photons acting at particles, and they do a random walk in the system here, and then they leave the sample in any direction. So the black part here can be explained by particle trajectories, whereas the blue part here, I need the wave aspect of the photons. In addition to this index of refraction and this particle part, there's a small peak here, which is coming from mesoscopic physics, so it's not explained by the average index of refraction, and it's not explained by particle physics. So it's a wave effect, and this is something which excited many people for many years, and we participate in this excitation by measuring this type of things. Okay, so this can be measured. So a recent experiment in collaboration with a group of Junji at Jilla looked at the cloud of strontium atoms around the forward direction, and this index of refraction enhancement here is shown up here. So this is a log scale. So you see a large forward scattering here due to this coherent scattering, forward scattering of all the atoms in this close to the same mode around forward direction. So this this effect here can be measured experimentally. We measured the other wave effect, which is called coherent backscattering, and this is explained by the following picture. So if you take photons which do random walk multiple scattering in the sample, we have to add up all the probabilities, amplitudes to go to the detector, and some photons will follow path number 1, some will follow path number 2, and these paths 1 and 2 are uncorrelated. So if I do a configuration average, the phase of the photon coming out along path 1 and 2 are completely independent, and this will average out to 0. But there's also some photons which follow the dotted line here, and which follow exactly the reverse path in the sample. So the path length difference in the sample is exactly compensated by construction. And so in that case here, I have to add up the amplitudes pairwise here, and this means if I go in the backward direction, I will always have a constructive interference like in a Sagnac interferometer. And so this, just a piece of white paper, any multiple scattering medium, acts like billions of Sagnac interferometers which are automatically aligned. So I don't need to touch any mirror. I have billions of Sagnac interferometers which are aligned. So this is nice. So we can measure it, yes. If I take my laser, I go on a white screen, I will see some scattered light. But even in the single scattering limit, I will have speckle pattern. We know that this wave will interfere in all directions. So if I see a speckle pattern here, as obtained from a piece of Teflon, I make a cut along one line, I see this. So now I do not know if this is interference in the single scattering limit or if there's any multiple scattering involved. And to get this information, I do configuration average. I rotate my piece of paper or Teflon, and I average all the signals, and I get this nice peak here. So now I know that there is interference in multiple scattering. So this is a signature of interference effect in multiple scattering, which cannot be explained by a simple index of refraction model. So it's a wave effect which cannot be explained by a simple index of refraction. So we did the same with cold atoms. So we replace our piece of white paper by our nice cold atom sample, a little bit more complicated to prepare, but basically the same result. We come with the laser here. We look around the backward direction, and so each pixel here on the camera, which is placed in the focal plane of a lens, corresponds to an angle in the far-field emission. And after configuration average, we see this nice peak. So even atoms which are excited on resonance do this interference effect in multiple scattering. So don't think that atoms which are excited on resonance do spontaneous emission and any phase information is lost. We know this is wrong. If we excite atoms at low intensity, there will be an oscillating dipole, and the phase information is not lost. It's elastic scattering, even on resonance with atoms, and this is a manifestation of this interference effect in multiple scattering, even if you excite atoms on resonance. Okay, so these are some examples where interference effects are manifest. There are many, many others, of course. Any type of Michelson interferometer will show you this. Speckle by itself is a manifestation of wave interference, of coherence of photons. If the coherence length of photons is too small, you will average out the speckle field. Even if you look at intensity correlations, so if you just measure intensities, and if you do what is called a G2 intensity correlation measurement, we did this recently in a cell of hot rubidium atoms, and you get this enhancement here. This shows that this is an explanation which requires wave interference. So it's a wave feature which gives you this enhanced intensity correlation function here. And we do this here, and this is related to the previous talk, where we want to do random lasing and we want to go to astrophysics. So this looks a little bit like the historical Henry-bound Twiss experiment, which we want to redo for stars. So that's why we do all these efforts here, going to nanosecond resolution and trying to optimize the techniques which are possible today, which have been evolving over the last 50 years. Okay, so far for the coherence of photons, we see many effects. Not everything is understood. For instance, in a disordered system, where we look at this multiple scattering, there's an open question which seems a little bit strange that so many years, 150 years after Maxwell equation, there's still open questions for Maxwell equation. For instance, is there endless localization possible for light? So I take Maxwell equation for a random medium. Is there endless localization possible or not? Are there endless localized state in this system? Some people say yes. So there's a paper here, a mathematical paper in the end of the 90s, and they say, if you look at the Maxwell equation, it exhibits endless localization. Other people, including us, which we follow this, say, no, this does not work. So there's still some controversy, even today, about the sheer existence of real endless localization of photons in a random system. Of course, there's some assumption in this paper, there's some assumption in this paper, and they're not the same, so there's still room for debate. So 150 years after Maxwell equation, many things still are open. So we still need work to be done to understand this. These two are theoretical papers, so we can turn to experiments. What is nature telling us? And it's not so easy to do this. The regime where we expect endless localization to happen is very difficult to reach. And let's say that the best experiment up to date has been done by the group of Georg Maret in Constance. And to say the status of today is it's not conclusive. So there's still some debate about this experiment, if this can be considered as a proof of endless localization of light. So we still don't know if this exists or not. So that's open questions which are related to the coherence of photons. Okay, so then we turn now the chapter and see, now I showed you what happened if an electromagnetic wave hits on atoms, and then I look at the light coming out. So now let's turn on the atoms. So what happens if I look a little bit more on the atoms? I forgot about the photons and look what happens to the atoms. And if you look at atoms, you have a different way of looking at things. And this has already been studied very well by Dicke in the 50s, so it's also a very old topic. For instance, Dicke showed that there are what is called super and subradiant states or superfluorescence, and so the idea of this is that if you take many oscillators which oscillate in phase, if they are close together, they oscillate like a big dipole, which is radiating much faster than the individual dipoles. And so there's a cooperative enhancement factor for this emission, which has been described by Dicke. And for an inverted system, this has been observed by Felt in the 70s for the superradiant, for the faster emission. So instead of having a spontaneous emission here, all the light comes out in a very fast burst of light. So it's a fast pulse of light which comes out if you reach this condition for superradiance. So this is nice. What we did is we tried to look a little bit new again on this type of physics. And so here again, I zoom on the picture which is extracted from the paper by Dicke. So if you take n two-level systems, you can build up all the Hilbert space of this, and there are many, many states. For instance, there's one state where all the atoms would be in the ground state, which is this state here. There's only one state like this. There's one state where all the atoms are excited. There's only one state like this. And then there's, for instance, n states where one atom is excited, but I don't know which one. So there are n states like this. There are n minus 1 over 2 states where two atoms are excited, and so on. And so you can build all this manifold of states. And so what Dicke showed, if you start from all the atoms inverted, the first emission here will decay n times faster than the single atom decay. This actually is not very surprising because you have n atoms. So you have n more chances to get a photon. So it's not very surprising to find this factor of n here. But you also find this factor of n here with a single photon excitation. So it looks very symmetric, but for me, this factor of n here is less trivial than this factor of n here. And the reason is that this factor of n here, the emission goes to one symmetric state here. And the faster emission here is only connected to one symmetric state. And all the other states are not connected to the ground state. So that's what we call the subradiant states. So they don't radiate as quickly as individual atoms. So there are some states which emit light very quickly, and other states which keep the photon for a long time. And so the idea is that this, for a pair of atoms, for instance, you would have two atoms. So if the two atoms are close together, if they oscillate in phase, they radiate faster. And if they oscillate out of phase, they keep it's a quadrupole, so it doesn't radiate as quickly. And that's the subradiant state. This quadrupole here is the subradiant, and this is the superradiant state. And so what has been shown by Dicke is if the system size is much smaller than the wavelength, then this factor n is you have an n-time enhancement factor here, where n is the number of atoms in your sample. Already in the paper in the 50s by Dicke, there was one part of the paper which is less well known about an extended volume. What happens if the volume is larger than the wavelength? Then the math gets very tricky, and there was no analytical expression how fast these modes would decay. More recently, there's been some effort to reformulate this, and in an extended cloud, actually, this emission rate here goes like what I call B0 times the single atom emission rate, and B0 is the number of modes you can patch on the surface of the sample. And so this looks like a cooperativity parameter, like in the cavity. How many atoms share the same mode? If I have many, many atoms which need to share the same mode where the photon can be put into, then there will be some interference effect between these emission processes. So in this case here, we have a cavity-less cooperativity. Like the random lasing part, you can get rid of the mirrors and do many, many physics which looks like cavity physics, but without mirrors. This is one example where you have a cooperativity parameter without mirrors. And so you can express that the superradiant lifetime increases like this cooperativity parameter, and this should be minimum. The lifetime of the long-lived modes decreases like 1 over this cooperativity parameter. So the larger the sample, the longer lived these modes would be. And so the problem is superradiance has been seen, as I showed you here, superfluorescence has been seen in the 70s. Subradiance in many, many atoms have never been seen. Why not? Because these are long-lived states. They're kind of metastable states. They're fragile states. So they need to be isolated from any non-radiative decay mechanism. So if you have phonons or any other mechanism which couple this state to the ground state or to the superradiant state, you will lose this subradiant line. So it's like looking like for a very, very narrow line, and these lines need to be this system needs to be well protected to be able to observe this narrow line. And so, for instance, this is a similar expression. If you increase the decoherence in this, if you would want to look at superradiance, fast decay, and then subradiance later on, if you add decoherence, then you will destroy all this distinction between superradiance and subradiance, and you just get independent atom decay. If you have a local decoherence phenomenon, then you know exactly which atom has emitted the photon, then you lose this wave interference effect. And so this is why I think that cold atoms are maybe not the only, but up to now maybe the best system where you can get a decoherence-free sample to look for subradiance. And so this is what we did. So we did some simulation to see what we expect in the experiment. And so we tried the experiment. So it's time-dependent experiment. You come with a laser, you switch it off, and you look how light goes out. Similar to what has been done by Georg Maret in white paint, where he was looking into this deviation from classical diffusion particle trajectories as an indication of underlocalization. So we look at similar signatures. So one important thing is that there are different ways to make a photon stay long in the sample. One is underlocalization, and there you expect the lifetime of the photon in the system to increase exponentially with the system size. So there you would look at the lifetime, which depends on the localization length of the mode, and if the sample size is very large, the photon does not touch the boundary and it lives longer. So it should be an exponential increase. You can also have multiple scatterings, like a random walk of photon particles in the sample. Then it takes the square of the sample size to diffuse out. So it's the diffusion process. And in the case of Dicke subradiance, what I told you is that this cooperativity parameter, which depends on the on-resonant optical thickness, so it's not detuning dependent as here. So it's a different scaling law, depending what type of mechanism you expect. Okay, so we do time result experiments, and we look at how the time constant will depend on the system size. That's the signature. Because having long-lived photons in the system, there are many, many ways to do it. So we did this many years ago in the initial attempt. So the first experiment done in Florence on multiple scattering and radiation trapping here. And so we improved a little bit the signal to noise and optical thickness in our sample. And what we saw is that the lifetime of the photon in the sample increases like the square of the optical thickness. So this was consistent with radiation trapping, particle trajectories in the sample, no interference effect. We found some strange things here about the transport velocity, but that's not the main issue here. So basically, at that time, looking at the dynamics of, we could go down to maybe a few 5% of the average value here. We saw everything consistent with radiation trapping. So that was fine at the moment. So we improved a little bit our experiment. So that was a long effort to have a very clean switch off of the laser here with a better than 10⁻⁴ dynamic range of switching of a laser. So switching of a laser very quickly, very well is not so easy. So no after pulsing by using some high-tech detectors and so on. Now we have we can look at signals at level to 10⁻⁴, which is crucial for what I will show you now. And these are our experimental results. So we look at the intensity when we switch off the laser. It drops, of course, and it goes to 0 at some end, of course, no surprise. But if you look at the last time constant we can measure here, there's long-lived states. So this is the time scale in units of atomic lifetimes. So we can get lifetimes 100 times longer than the single atom would decay. So it's a huge increase in lifetime. And if we change the optical thickness, the on-resonant optical thickness, the slope here changes as expected. If you change the tuning, the amplitude changes here, but the slope is not changing. And if we plot all this data, we have plenty of data on the single plot, we find that the lifetime of these long-lived modes here increased linearly with the on-resonance optical thickness, exactly as expected from Dicke subradiance. So we interpret this as an experimental observation of Dicke subradiance, which is a necessary counterpart of superradiance, but difficult to observe. Okay, so this is, if you look at underlocalization, we were looking at coherence of photons. Now we look at coherence of atomic states. So it's still a question, how can we jump from one to the other? Can we still do underlocalization of light? Now we seem to favor the Dicke type of physics because the atoms are well isolated, and if the coherence of the atoms is well protected, maybe Dicke wins over Anderson. So it's still not completely clear. We have some idea how to reconcile Anderson and Dicke. Basically, if we assume that this well-protected atomic coherence allows us to have photons which live in the system for a very long time, then those photons, they don't know that the world is an open quantum system. They don't know the outside of the world. So it's like a Hamiltonian system. It's a closed box. And in a closed box, that's where the Anderson model was developed for. Anderson model was not developed for an open system. It was developed for a closed system. And the subradiant states, they live in a closed system. So by adding additional diagonal disorder, we have some indication that we might be able to reproduce underlocalization of subradiant states. But for this, first, we needed to find the subradiant states, which we now have. And so to conclude my talk. So there's still open questions for the coherence of photons atoms, like Maxwell equation with strong disorder. It's not clear. Going from microscopic atomic description to a dielectric description of the medium, an average description, index of refraction, it's not clear. So there's a challenge for theory how to reconcile like Hamiltonian or atomic physics description to mesoscopic description, where they have ladder diagrams, some models which work very fine, which seems to be very efficient for Anders localization, but it's not completely understood, or to macroscopic models. And there's also, of course, a challenge for experiments. What material should we use to study this Anders localization? White paint, cold atoms, whatever else, I don't know, maybe there's structured materials which might be more appropriate. And what are the right signatures? Maybe looking at the time constant decay is not the good signature to have the smoking gun for Anders localization. So there's still a challenge for many things, which is nice because we have a lot of fun and a lot of experiments can be done, and the discussions will be ongoing. And with this, I thank you for your attention.
Okay, questions?
Robin, it's extremely stimulating. You seem to be on the side of people who say that there cannot be Anderson localization with light. Why? It's because of the vectorial character? Because okay. Anderson localization with scalar wave, there is no doubt. It exactly. Does exist, okay? So why shouldn't it exist with electromagnetic waves? Because of the transverse character?
Yeah, so, okay, so the status of the art, so we're working with Romain and Carlos, I know, on a 2D model where we can understand a little bit better what is happening. The theory which has been done up to now is based on an analysis of eigen values of an effective Hamiltonian. This is what Sergei did, this is what we did with Eric Ackermans. So it's, we define, so in Anders localization initially was looked at to look at the transition between a conductor and an insulator. Okay, so the first question is, this is not equivalent to look at if there are localized states, because if I can go through the system here via some states, let's call them super radiant states, but maybe other states, which are not localized. It's enough if I have some open channels which cross the system, and then I will not have an insulator, which does not mean that there are no localized states. So depending... Exactly. Yeah, in the lower block band, and then you look at the propagation of the wave, where the amplitude goes, right? So, so what Taulis did is he connected the analysis of the Anderson model to transport properties, and so they defined the conductance, which is something which looks like what we're doing right now, or what Sergei Skipetrov is doing, but it's not the same. The function we define, or Sergei is defining, is not a transport property function. It's a spectral overlap. It's the width over the distance between eigenmodes. So it's not clear yet if this function can make a difference between super and subradiance or Anders localization. First thing. So even in the scalar limit. And for Anderson, for the Dicke picture, it's known in the 70s. That what was called the van der Waals dephasing problem, what Serge Roche or the Rydberg people looked at. If you look at a symmetric state is a symmetric state for some symmetry of the operator. If you have 1 over r cubed or 1 over 6 other Hamiltonians, they do not respect the same symmetry. So the symmetric state for the long-range interaction is not a symmetric state for the near field. So if you have different symmetries in the operators, this might destroy the global properties for super and subradiance. And this might be an explanation why scalar and vectorial waves behave so differently for Dicke. And the question, what do you see, if it's Dicke or Anderson, it's not clearly solved yet in the literature. We try to work on this, but I think that there's indeed the near field part, which is, for sure, the near field part makes a difference from scalar to vectorial models. If you would have scalar photons, we would be obtaining the same results as you get in matter waves, almost no doubt. if we could do the experiment as you do, like starting with photon in the sample and see how it spreads. It's not like coming from the outside and looking how it goes through. Yes, nothing in 3D. Only quasi 1D or nothing in 3D. With the, no, that's in the tube, and this is quasi 1D experiment by Genack, as Genack. It's quasi 1D. And it's micro, well, but it's electromagnetic wave, Maxwell equation. Maxwell equation, I agree. But it's a quasi 1D symmetry. By the way, the experiments on other waves, so it's a general property of wave equation. So the matter wave is, you can produce purely scalar. It's scalar. Acoustic wave is a different story. Even there, it's we can discuss, but the acoustic wave, it's for me, it's clearly not clear. It's what happens in the acoustic wave. It's they mimic hopping from one sphere to the other sphere because the coupling is by the sintering between two spheres. It's not due to the propagation of the wave equation in between the spheres. No. Exactly. Yes. This is we can go into the. I say it openly, so you can cite me. This is not simulating the wave equation, localization of wave equation. What they do, they see Anders localization in a network, hoping in a connected network, but not in the wave propagation. Oh, yes. No problem. I don't claim that Anders localization does not exist, but for light or electromagnetic, in the framework of Maxwell equations, that's a different, that's the open question, at least the one I address.
Okay, more questions? Well, if you have a question, no? So let's thank Robin again. I think we will have a break now, right? How many minutes? Okay, 10 minutes?